Okay, so today we're going to be doing 5.1b, which is estimating with finite sums. And some of these are unevenly distributed, so we'll talk about how that differs from what you learned about yesterday.
Hi, Kashi.
So, we know that when we have a situation where we have even distribution, we can use this formula, okay, to get the sum of the heights, or to get the area of the total space. So let's go ahead and practice one of the problems we kind of learned about yesterday, but I feel like we didn't get a lot of practice with midpoint because that's the one that we didn't really do as much. So let's go ahead and do some midpoint problems. So it says here, a major retailer once studied the rate that people entered their store any given day of the month in December. The rate that people entered the store, given in people per hour, is listed in the chart provided. Use the midpoint approximation method with 6 subintervals. So 6 subintervals, that means that's going to be 6 rectangles. So subintervals is like how many gaps there are, basically, is what they're saying. Of equal length, so they have to tell you that, to determine the total number of shoppers that enter the store in a single day. So you're going to notice there's a whole lot more data points than how many we're working with here. So if we're talking about 6 rectangles, how many data points?
7.
Yes, 7 data points. Very good. We're working with a lot more than that. So what that means is we're going to have to break this up because we're talking about in a single day, that's from 8 a.m. to 8 p.m. So we're going to be breaking this up a little bit differently.
There are 13.
Yes, there are 13. So what I'm going to do to make it easier for me to understand, it gets confusing to me when we have 8 and 8 again. So I'm going to convert these to military time. Just because it's less confusing to work with when I'm dealing with numbers. Does everybody see what I'm saying by that?
Mm-hmm.
Okay. So everybody knows how military time works. You just add 12 to all the ones that are smaller than 12. All right. So I'm going to create an interval that's just going to help me understand how everything's laid out. So I know that we start at 8 and we end our day at 20. That's the same thing as 8 p.m. And we want to break this up into 6 subintervals. So we're going to break it up in the middle. And then each of these also need to be broken up, again, 2 times, evenly spaced. That will give me 1, 2, 3, 4, 5, 6 subintervals. Does everybody see why I need to break it up that way? So we do have a middle point. So what's the middle between 8 and 20?
14.
14. And then from 8 to 14, if we have 2 gaps, it's going to be going by 2s, right?
Yes.
18. So these sectors represent my rectangles. We're not going to actually draw the rectangles. We're just going to kind of visualize what's happening here. So we know that we're going to have some rectangle between 8 and 10, okay? So that's going to encompass these data values right here, these first 3. Now we're dealing with midpoint approximation. So are we going to use the left end, the middle, or the right? The middle of 1,000 is going to be the height of that supposed rectangle. Okay, we don't need to actually draw it. We're just going to represent it by the 1,000. And then what would be the width of this interval?
3,
2.
2. 2.
Yeah.
From 8 to 10.
Right.
10 minus 8 is 2.
It's not 8, 9, 10. Okay.
So the next interval, you're going to notice these intervals do overlap on the ends, okay? The next intervals, because they're all touching, is going to be from 10 to 12. So it's going to be 700. And the width is still 2. And then from 12 to 14, that's these guys, the middle number is, good. From 14 to 16, my middle number is 700. And the width is still 2 for both of these. And then from 16 to 18, 900. And then from 18 to 20, 1100. So see how you don't have to actually draw the graph to get a visualization of what's happening. If it were left, we would have used the first value. If it were right, we would have used the last. So now, you could either multiply each of these individually by 2 and add them up, or we can just do the whole thing times 2 and add them up, correct? 'Cause it's going to be the same operation either way. Now, you know that rule b minus a divided by n? You could have used that here too. It would be 20 minus 8 divided by 6, which would also be 2. So multiple different ways to get that number. So we do that big calculation. And we get this. Now let's talk about what this actually represents. We took a range of time and we multiplied it by a rate. So time is in hours here, right? Hours times people divided by hour, right? Because that's the rate. What's going to happen when I have hours divided by hours? So this represents people. So that's the mathematical logic behind why it's people. Yes?
So is it always just going to cancel? So you don't actually need to do that. It's just okay.
No, you don't have to. That's just more for me to show you like the reasoning.
What it is.
Yeah. But yeah, that's correct. Any questions about this one? Okay. So basically that just means that if we estimate there's this many people that went through the store. Yes.
So because you overlapped the 900, is it because it's the middle, it's right and right and middle? Is that why?
Exactly. So as we move on to intervals, what was once the right end of the one interval is the left of the next.
Oh, okay.
Does that make sense?
Yeah.
Okay, perfect. All right, so sometimes we're going to deal with situations where we're not dealing with an evenly divided set of data values. So do you see how here with these data values, see how we're going up 7, up 5, up 8, and it's not consistent? But this is what we have to work with. We don't have a function to get exact values, so we can actually create an unequal distribution with the rectangles for the Riemann sum. Okay. So step 1 is I'm going to connect this curve. It just helps me visualize what's happening. And then we're going to break it up. It says estimate the area under the curve from 0 to 5 using 5 left rectangles. So they didn't say evenly distributed. So I know I'm going to be working with the data values they give me. So if I'm dealing with 5 left rectangles, how many data points do I need?
4. Wait, 6.
6. 1, 2, 3, 4, 5. Look at conveniently they gave me 6. Okay, so that's perfect. That's what we need. So we're dealing with left rectangles. When we draw this, it's always going to be the height of the left end of that interval. So our first interval is going to be from 0 to what?
7.
7. Our next interval is going to be from 7 to 12. The next one is from 12 to 20. That's a big one. Next one is from 20 to 26. And the last one?
26 to 30.
26 to 30. So those are going to be the widths of my rectangles. Okay. So for the first rectangle from 0 to 7, what height am I going to go with that rectangle? 30, because that's the left end point. From 7 to 12, what's the height going to be?
36.
36, because left. And from 12 to 20?
43.
43. From 20 to 26?
48.
And the last rectangle? 44. So we're going to get into this more tomorrow, but do you see how it's an under approximation when the graph is increasing, but when it's decreasing, it's in?
Over the mark.
Yes.
So wait, how do we know we're using left for this one? Is it because it starts at 0?
Only because they told us to use
okay, I
left.
didn't see that.
Yeah, they would have to tell you left, midpoint, or right.
That's all I was going to tell you.
Always.
Okay.
Yep. Unless I say pick whatever one you want. But otherwise, yeah, it's going to have to tell you. So now we're going to calculate our area. So what is the width of the first interval? Good. And its height?
30.
Good. plus
What's that, 5?
5 times
36.
36 plus
8 times 43.
mm-hmm.
6 times 48.
Good. And lastly,
4 times 24.
so keep in mind what you probably have noticed is you don't actually really need to graph it. You can if you want, but when it's left approximation, it's going to use the first 5 data points. When it's right approximation, it would use the last 5, right? Because that's how the heights go. So you can draw it every time if it helps you like see the visual. I would recommend drawing it until you get really comfortable with
You
the
should
process.
make us have to graph it on the test, and grade our graph.
You want me to make you have to do it?
Yes,
Brian?
Okay, I'll be sure to do that.
it's
then.
easy.
Brian?
It'll give us 3 points.
Brandon, the question is,
I don't think
someone
it's
who
gonna give us
don't
3 points.
understand how to graph.
Well, that
So
sucks
3
for
points
that.
for you.
Yep,
less
3 points for me.
us.
That's all that matters.
So
I don't care
that's
about your guys'
Brian, that
points.
window.
1,198. And what's the units on this?
Feet?
Feet.
No, just feet.
Just feet. Because we're
It's over
multiplying.
that column.
Now, somebody was asking me, isn't this technically area? Why is it not squared? And this is a whole, like, rabbit hole of reasoning behind this. So I'll just kind of briefly explain it to you. If we were to calculate the area of any of these individual rectangles, you would say it's area squared because we have 2 units. But when we're dealing with area under a curve, we're not talking about 2 dimensions being multiplied together. We're just talking about total area. It's a very weird thing to think about because you guys are only used to thinking of area as something times something else. This is a whole different ballgame. This is talking about the total area of something underneath something, how many feet it spans. Okay, so I know it's kind of tricky to think about, but you'll get the better understanding more when we go into integration. So any questions about that one? Okay. What does the area represent in the context of the problem here? What do you guys think?
How many feet the cars travel?
Good. Total feet traveled. So area under the curve may be area, but it represents something else that is not area. Does that make more sense?
Mm-hmm.
Okay.
Well,
Yeah.
because it's not like, it's
It's
not
not a
making
3D
like an
plan.
area thing, it's just making like a straight line, it's straight-ish line, it's not, it won't.
Well, it's
it may
just
not be
the-
an actual straight line.
Yeah, so we're using area to help us calculate something that's not area.
So yeah, you're like using the 2D thing to calculate a 1D.
No, 3D thing, calculate 3D.
You guys can really, you could really go